this video is going to walk through the steps of Activity 3, hopefully help for those of you who had a little trouble with this, particularly finding the p-value. So first of all, this activity is based on a study published in Psychonomic Bulletin and Review. The study claims that people use facial prototypes when they encounter different names. To assess the claim, study participants were given two faces and asked to identify which one was Tim and which one was Bob. According to the researchers, the participants overwhelmingly agreed on which face belonged to Tim and which face belonged to Bob. However, the researchers did not include the actual marks and results from their study. So in this activity, we collected data ourselves to use it to test the claim that a majority of people agree with which face belongs to Tim and which face belongs to Bob. We are going to use a 5% level of significance for our hypothesis test. So each student in class collected data from a sample of 5 people. Each person was shown the same 2 pictures of men's faces used in the original research study, and were asked to assign the name Bob to one photo and Tim to the other. For each volunteer, we recorded the name that was assigned to the picture on the left. So first of all, first question is, what are the cases in the study? The cases in a study, remember, are the individuals from which the data is collected. So each person who is asked to decide which face looks like Bob and which one looks like Tim, each of those people that we collected data from is a case in our study. What is the variable? Now the variable, remember, is the piece of information that we collected from each of our cases. So from each person, we asked them to assign the names, and what we collected was the name assigned to the picture on the left. So that is our variable, and it is categorical. Okay. Whoop. Let me come back. Okay, so now we want to know if a majority of all people would assign the same name to the person on the left. So our null hypothesis is going to be that that is not the case. Not a majority assign the same name. To the face on the left. And our alternative hypothesis is going to be that that is true, that a majority assign the same name to the face on the left. Okay, so there are our hypotheses. Now the next thing we did is we actually collected the data and entered it in the Google form. And next we're going to take a look at the sample information. Data were collected from 77 people, so that's our N. Out of the 77, 50 put Tim's name on the left. So the proportion that put Tim's name on the left, our sample proportion, p hat, was 50 over 77, which gives us a sample proportion of 0.649. And when we conduct our analyses with just one categorical variable, with 2 categories, we generally pick one of the 2 categories to think of as a success, and then focus our analysis on the proportion of successes. It's arbitrary which one we choose as a success, but in this case we're considering Tim on the left to be a success. So now we're going to revisit the hypotheses that we wrote earlier, but we are going to write them again, this time using the parameter p equal to the proportion of all people who would put Tim on the left. So, going back to look at our old hypotheses. The null hypothesis is that it was not a majority assigned the same name to the face on the left. So if there's not a majority either way, then that would mean that the proportion would have to be the same who would assign Tim and who would assign Bob, and so that's going to give us a p equal to 0.5. The alternative is that a majority assign the same name to the face on the left. Now that could either be more people assigning Tim or more people assigning Bob, but it will mean that the proportion assigning Tim to the name is not equal to 0.5. So we can rewrite these hypotheses as our null hypothesis that P equals 0.5, there's no majority either way, and our alternative that P is not equal to 0.5, that whichever way it goes, more Tim or more Bob, it's a majority in one direction or the other. So it's a two-tailed test. I know it's two-tailed because I'm looking for more Bob or more Tim, and I have a not equal to sign here. So this is two-tailed. One more thing I want to say about that. Now, I can see in my sample that the proportion who said Tim was on the left is higher than Bob. So why am I not doing a right-tailed test? And the reason I wouldn't do a right-tailed test is because my hypotheses should be based on my original research question, not on my data. So since my original alternative hypothesis that the majority assigned the same name to the face on the left, not necessarily more to Tim, either way, my hypothesis should reflect my research question, not my sample data. So it's two-tailed. Okay, so now we want to find the p-value for our hypothesis test. To do it, we're going to simulate the randomization distribution, which is going to show us how likely it would be to observe a sample statistic as extreme as ours if the null hypothesis is true. So the assumption that we make about the null hypothesis when we simulate the randomization distribution is that the null hypothesis is true. Otherwise, we can't figure out what the chance is that we'd see our statistic if the null hypothesis were true. We need to know what kinds of things would happen by chance if the null hypothesis is true. So our assumption is that the null hypothesis is true. So I'm going to go to StatKey and simulate the randomization distribution. So here in StatKey, since we're doing a test for a single proportion, I'm going to edit the data to reflect my own data. We had 50 who said Tim on the left out of 77 total sample size. We can see that our original sample shows over here. It reflects that proportion is the same as the one we calculated from our data before. To check and make sure my null hypothesis is the same as in my hypotheses, and here it is, it's 0.5, so that's perfect. And now I can generate samples. So I'm going to generate 5,000 samples in my randomization distribution. And now this is showing me the types of sample proportions that might happen by chance. If really among all people there's a 50-50 chance that someone would assign the names Tim and Bob to the guy on the left, what's the chance that I would get a sample statistic like mine? To figure it out, what I'm going to do is look for my sample statistic in this distribution. I can see 0.649 is somewhere around here. I can see it's something that does not happen all that often. So it's unlikely that this happened by chance if the null hypothesis is true. Coming back in, we want to know what does each dot in the randomization distribution represent? Well, let's look at it. If we click on one of these dots, we can see over here on the side what it's showing us. It's showing us the sample that generated that. So you can see we've got, like at 0.6, if I click on a dot, it shows me a sample with a proportion of 0.597, very close to 0.6. So what these dots represent is, and here's another one, click on this dot, oh, that's a sample with a proportion of 0.519, and look, it was here at 0.519. So what each dot in this distribution is representing is the sample proportion calculated from one sample of 77 people, assuming that each person has a 50% chance of putting the name Tim on the guy on the left. Now we're going to need to find the p-value to measure how strong the evidence is against the null hypothesis. the p-value is the chance of seeing a sample statistic as extreme as ours or more extreme if the null hypothesis is true. So to find it, we're going to find the proportion of simulated results that are equal to our sample statistic, which was what was it again? 0.649. 0.649, or something even larger, okay? And then we're going to multiply by 2 because it's a two-tailed test. So to figure out the proportion of dots out there, I'm going to come back to StatKey. I'm going to click, since it's a two-tailed test, I'm going to click the two-tail option. I need to figure out the proportion of dots at my sample statistic or beyond. So I need to change this cutoff down here to my sample statistic. 649. And now it's showing me the proportion of statistics that are out at 0.649 or beyond is 0.0066. And when I want to find my p-value, I'm interested in both tails. Whoops. So I'm going to take this and add it to what's in the other tail, which is the same thing as multiplying the one tail by 2. So I'm going to take my 0.0066 and I'm going to multiply it by 2. This gives me a p-value of 0.0066 times 2 equals 0.0132. What that is telling me is that the chance of seeing a sample proportion that's as far from 50% as 0.649 or even farther away, if the null hypothesis is true, would be 0.0132. So it's really, really unlikely that we would see a sample like ours or more extreme if in fact people were equally likely to put the name Bob and Tim on the guy on the left. Because this is something that probably wouldn't have happened if the null hypothesis were true, this small p-value, less than our significance level of 5%, is going to lead us to reject the null hypothesis. So we're going to reject the null hypothesis because our p-value is less than our 5% level of significance. What this means is that we have strong evidence in favor of the alternative. So there's strong evidence that a majority of people assign the same name to the guy on the left. And this supports the idea that people use facial prototyping. I hope that me walking through this activity helps you as you're reviewing. If you find that you still have questions, please let me know. I'm happy to talk with you about it. Have a good day.